Hello, everyone. Just screen here for people joining. Okay, let me screen. So please let me know if you can see the slides, please. Perfect. How are you guys doing? Yeah, surviving the semester. I think it's good that this is last week. So hopefully things will go smoothly in the next few weeks with the exams. And so, okay, so anyone have any issues with reviewing the material, like any major things? Have you guys started looking back and wrapping up all the problem analysis and stuff like that? Any comments? Question is in the wrong time, I guess. Still catching up with the rest of the semester, I guess. Okay. Oh my God, that's the same questions as last time. We talked about this last time. Let me repeat again, just to get you guys understand, like, you know, the fluid mechanics part is kind of connected, right? So stuff that you learn in the first chapters will help you to go and like, you know, solve a problem on the last part of the course. But specific problem on chapter 1, 2, and 3 will not be, like, analysis problem will not be part of the exam. So starting from chapter 4, you will start getting problems specifically on those chapters, and then lots of conceptual questions about everything you have learned in the course. I hope this is helpful. Okay. Be posted for chapter after? No, no problem after chapter 11. So the material of the course should really cover the flow and viscous flow and piping and some concept in the pumps. But for chapter 7 and 10, it's mainly we're trying to just go over, like, you know, go briefly and provide overview on some conceptual ideas. So expect, like, you know, maybe multiple choice or true and false on these chapters as well. Okay, so one page double, yeah, yes, that would be fine. You can prepare whatever, like one page both sides with any stuff that you are like to remember. Anything that is very specific, like, you know, chart or something like that, it will be part of the exam. Like, so if you need to find something like a pump performance is going to be provided in the exam and stuff like that. I don't know. Lian, please, you know, maybe go again to the recording and you'll see I talk about this before. Thanks. Okay. Okay, so let's start talking about chapter 7. So as I mentioned, we're going to talk briefly on this chapter, and the most important element in this chapter is just to understand what is involved in flow around immersed body, right? We talk about immersed surface when we talk about the pressure distribution in static fluid, right? We are talking here about, like, you know, something different where we have a certain body that has a certain surface and the fluid is going around this surface, right? So three main idea that we need to understand in this chapter. The first one is, what is the purpose of studying the flow around immersed surface, or you know, flow around bodies, and also get to know briefly what is a boundary layer what is the definition of boundary layer. We're not going to get into the theory of the boundary layer and how to do the analysis, but at least understand when we talk about boundary layer, what it meant by boundary layer. And then the last part is just to give you an idea about the drag and the lift, what is the forces that we are talking about in terms of drag and lift on for the flow around bodies. Application, and as I used to do that for every chapter, that you have to think about what is this has to do with an industrial application and real type of problem. You might see lots of flow around surfaces, including the flow around like airplane or flow around buildings, flow around wind turbine. It doesn't have to be only gas, it could be liquids, for example, the liquids or the flow around the surface of a ship. So all these type of flow is considered to be an application of the material that is covered in these chapters. Not only these, but also flow or wind around electrical cable, or the flow around human body, or even equipment that is running in on your computer for cooling and reduction of heat transfer in these equipments. Many applications actually for the flow around surfaces, or flow around immersed surfaces. And immersed mean it is surrounded by the fluid. So we're talking here about the external flow. So many questions will arise from looking at this application is for example, what will be the wind speed and location of this wind turbine? And how big is this wind turbine blades and so on? These questions will always be available when you are really designing a wind turbine machine. Also, what energy expected to overcome drag over cars, for example, or airplane or submarine or ships, right? So flow around these type of bodies is contribute to the resistance of these machines to move, or this equipment or these bodies to move. So we need to know what will be the forces acting on these bodies. Or fluid, what is a velocity over a building roof, so or stack, the flow around the stack for in these buildings. So many applications require some knowledge about the fluid flow around these bodies or services. Also, for example, here, electric cooling. So what will be the force or the power required by the fan in your computer in order to supply this amount of heat transfer by convection in these equipment. And also stress, shear stresses and erosion in rivers, when we're talking about fluids flowing in rivers and or oceans, and so on. So many questions actually is dealing with fluids on the external surfaces. Okay. So whatever resistance that we are talking about here, surface resistance here is talking about fluid that is flowing around the surface. It will kind of exert a certain force. We call it the drag force, and the drag force here is basically representing the resistance force that is resisting the body to move inside these fluids. Okay, and the drag mainly consists of two types of forces. One force is, we call it the shear force, or the skin friction drag. And the skin friction drag is related to the viscosity, right? Because we know that for the fluid to move, we can imagine this fluid is in the form of layers, and these layers had lots of friction between the particle of this fluid and itself. And the property that we discuss in the first chapter is referred to as a viscosity. So in this case, we are talking about viscous or friction drag. And in this case, we are dealing with what we call it the drag force. In terms of shear force, we call it the skin friction drag or friction drag. Other forces that also can apply because of the fluid around the surface is the pressure forces acting on the surface, right? So we've seen that when we talk about the statics or the hydrostatic forces on immersive body, but at that time the fluid was stagnant. So we only had pressure forces, static pressure forces. But imagine now if we have a fluid flowing and just hitting the surface. So we might expect some kind of forces coming from these the distribution of the pressure around these bodies. So when we have a fluid that is hitting a surface, we say that, if you remember in chapter, I think chapter 5, chapter 4, when we talk about the velocity in the Bernoulli equation. So every fluid going on a certain direction, there's three forms of energy. One form is a pressure energy, the kinetic energy, and the potential energy. So now if there is a fluid that is moving and then hitting a surface and stopped, it means that part of the energy converted to a different form of energy. For example, the fluid dynamic or the kinetic energy convert to a pressure energy that is creating some distribution forces around the surface. So the other type of drag, we call it the form drag. And the form drag here is basically related to the pressure distribution around these surfaces. One thing to remember for shear forces, that shear forces are always in the fluid mechanics are related to the viscosity and the velocity gradient that is created by this change of the velocity between one layer of the fluid and the other layer. Okay. That's why we need to, in this chapter, to get an idea about what is a boundary layer. Okay, what is the definition of the boundary layer? And the boundary layer is defined as basically the first few layers of the fluid that is in touch with the surface itself. This is where we are interested to find out, what will be the friction forces affecting the surface. Unfortunately, we don't have time to really cover the boundary layer theory, but at least you should get familiar with what is the concept of the boundary layer. So when we are talking about boundary layer, so in this case we have, for example, a wing, like a cross section of airplane wing. So if we consider this is kind of something like this. So, and now we're just looking at the cross section. And so this is a cross section of an airplane wing, right? And we monitor the fluid that is going around this wing. So we have a fluid that is going from the top, fluid going from the bottom, right? And if we look at a certain point here, and this point here, we just try to find out what will be the velocity distribution around this wing, the velocity at the surface. Okay, so imagine this is a fixed and the fluid is moving. So the fluid is moving with a velocity, and this is fixed. Okay, so let me ask you a question now. At any point in this surface here, what will be the velocity at the surface? 0. And why is that? Remember one of the very important assumptions we did in chapter 1? No slip. Excellent, right? So when we have a surface and the surface is the fluid is in contact with this surface, we assume that the fluid will take the same velocity of the surface, right? And basically based on a non-slip condition. So in this case, the velocity here will be 0. And as we go far from the surface, what will happen to the velocity in this case? It will increase, and basically, it will keep increase until a certain point here where it's completely far from the surface, that is not even seeing the surface, right? So you can imagine now we have two type of region of the fluid around flow in an open or in a free surface here. We call this as a free surface because this fluid here is very far from the surface that doesn't even see the impact of this surface. Okay, so the layer where the velocity is changing. So if you look at this, you magnify the velocity distribution here, the velocity at the surface is 0. And as you go far from the surface, the velocity is increasing, increasing until a point where the velocity is not changing. Okay. So if the velocity is not changing, right? So no change here. We call this is basically the free surface. So the layer where the velocity is changing from this point here to this point here is what we call it the thickness of the boundary layer. So the boundary layer is basically, is the area or the multiple layer of the fluid where the velocity is changing from the surface velocity to what we call it the free stream velocity. Okay, so the free stream velocity is basically the velocity that is far from the surface, that is not really seeing the impact or the resistance, due to viscous forces between the fluids because of the existence of the surface itself. Okay, so we can basically say that boundary layer is this region where there is a viscous effect of the fluid velocity in this layer of the fluid in contact with the surface. Okay. Sometimes we refer to the free stream or the fluid that is far from the surface. We call it inviscid flow. And inviscid flow here, it's not really an inviscid flow like as per se, but it's kind of assuming there is no viscous effect in this case, which means that if there is no viscous effect, if you remember in chapter 3, we called if the viscosity is 0 or there is no effect of the viscosity, that means we can consider the fluid as an inviscid flow. Of course, yeah. Imagine we're talking here about. Imagine we're talking about the wind coming over a city, right? So we can imagine that of course, the boundary layer for the on this big scale is going to be much big compared to the boundary layer over an aeroplane wing, right? So now if you are talking about the wind that is very far, at the very high elevation from the buildings, this can be changed with time, right? Depend on the massive wind that is coming, and inside the boundary layer where we can actually see some variation of the velocity between the ground surface and maybe at the top of the building, we can imagine that this value will change depend on the free stream velocity as well. Oh, be an ideal fluid, right? The flow, yeah, we don't say the fluid is ideal, but the fluid can be treated as an ideal flow. So the assumptions of an inviscid flow is where the velocity is not changing. Okay, so the idea in this chapter is to separate the topic. One topic is related to the fluid very close to the surface, so we are dealing with fluid layer very close to the surface, and then the fluid layer outside of this layer. Okay, so and that's why we say that this is the edge of the boundary layer, right? So the boundary layer will be only inside this region here, and outside of this we call it the free stream velocity, or there is separate chapters talking about this type of flow. We call it potential flow. Right, so we're talking about the flow that doesn't have any viscous effect on its its motion. So the velocity distribution is uniform in this case. Okay. So again, if we are doing this over a surface, of course this surface will have a beginning, a first point. So this surface here is not an infinite surface. It starts here and end here, right? So if you're looking at just before the fluid coming, imagine this is your wind speed, right? Once the fluid is coming into the surface, you might start seeing velocity distribution. So every time you are measuring the velocity, so here the velocity is same velocity of the plate, and let's assume it's u here is 0. So the velocity here is that much, and then after that point, the variation here, and then after that point, it's constant. So we can say this is the limit where the boundary layer is. At another point, the velocity changing until a certain point where there's, you know, there is no variation. So I can put another point, another point, another point, another point. So all these points are basically related to the point where there is no more change of the velocity along the, you know, or away from the surface. Okay, so we can plot a curve here, and this curve we call it the boundary layer. So inside this region here, velocity are changing. You can see here, after this point, the velocity is almost, you know, constant, right? So we call it the free stream velocity. Okay, and inside this boundary layer here, there is variation of this velocity because of the viscous forces between the fluid layer and itself. Okay, we call the distance, or the, you know, the thickness at any point. Of course, if this is x direction, okay, x here is 0 at any x, right? So for example, here at this x here, we call this distance here is, we call it like, you know, the boundary layer thickness. Okay, and this boundary layer thickness is changing along the x direction. So we're exactly along the, you know, the surface we are, right? Those are the terminology I wanted to be aware of, right? So just general knowledge about the boundary layer and you know, flow around surfaces. Things can be like, you know, expanded later on when you are interested in studying this type of topic. We know that Reynolds number, if you remember in chapter 5, when we said that we can, if for any complex problem, when we try to relate those parameters together, we can, you know, put the, you know, grouping of the viscosity, like, you know, the velocity, the distance, you know, and then we put all these in groups, and then we find out some non-dimensional parameter that affecting the flow, right? Of course, in the boundary layer flow, or the flow around immersed body, we are expecting the Reynolds number to be like, you know, a huge you know, factor affecting the fluid and the boundary layer thickness. So you can imagine here, this is just giving you an idea about, this is rho v and x here, because the distance, there is no diameter of a pipe, but the distance here over mu. So Reynolds number here is, if we have Reynolds number that is, you know, small value, that means we are expecting the fluid to be similar to the laminar type of flow, right? And you can see here, you know, in this case here, when you are talking about the velocity distribution at any point, the velocity changing, and then become almost constant after that. Okay, so inside this layer here, you might see, you know, the distribution here similar to the, you know, the laminar flow in the pipes, right? So, but in this case, it's going to be an external flow. So the velocity distribution here is taking what we call it the laminar velocity distribution shape, right? And you can see also here that the, you know, the thickness of this boundary layer is much, you know, bigger than, you know, when you have a turbulent flow here. So if you have a Reynolds number here that is equal 10, and 10 here is very small number, right? And here, like, you know, Reynolds number here is 10 to the power 7. So in this case, very high Reynolds number. So in this case, we have, for example, here the boundary layer here is very small. Why is that? Because of course the momentum, you know, that we have for like a very high speed flow, you might see the boundary layer becoming a smaller, right? Because in this case, you know, all the variations is happening on a smaller kind of boundary layer thickness. And in this case, again, like, you know, we can refer to the boundary layer, you know, in different names. One name is, we talk about it as a laminar boundary layer. Some other, you know, region where we are talking about it as a turbulent boundary layer. There are many, you know, analysis for the boundary layer thickness. The very common one is relating the boundary layer thickness at any location X as a function of Reynolds number. So you can see here this Blasius equation here that is giving you delta over X, and delta here means thickness at any X, at certain X along the, the surface is equal 5 over Reynolds number, or the root square of Reynolds number. So you can imagine that those boundary layer thickness can be developed experimentally, like or using some kind of analytical approach to relate Reynolds number and boundary layer thickness. This can be done for laminar flow and for turbulent flow as well. Okay, just to keep in mind that this is something that if you are interested later on to study, you are expecting to see the Reynolds number impact on the boundary layer thickness using some of the analysis available in these topic. And all these type of analysis will start from, if you remember the part that we skipped in chapter 3, when we talk about the Navier-Stokes equation, or the differential form of Navier-Stokes equation, or the momentum form and the differential form, right? But in this case, for a boundary layer, we can apply the same thing, and then we know that the shear stress is a function of the viscosity and the velocity gradient, so we can actually connect all these relation together to find out the boundary layer equation. Okay, that's not part of what you need to study, but at least you know that momentum, mass, momentum, and energy equation are all the time the three main governing equation for developing any relation in the fluid mechanics. So for a boundary layer equation, we also use same three equation in order to develop relation between velocities and pressure and shear stresses and so on. When we studied chapter 5, because we didn't study the analysis using the differential form, but we studied the analysis using what we call it the dimensionless analysis. Okay, we relate the drag around the sphere by putting the parameter where this drag is affecting. If you remember one of the example that we solved in the lecture, we said, okay, the drag force or the resistance force on the sphere is a function of the diameter of the sphere, the viscosity of the fluid, the density of the fluid, right, and the velocity of the the fluid around the sphere. And then we develop a relation for the drag coefficient without talking about the boundary layer. Okay, because we were interested in a global analysis for this. And if you remember, we said that the non-dimensional form of or the drag or the pressure coefficient will be much easier to handle when you are doing experimental type of work, right? So if you are dealing with a fluid around, for example, a sphere or a cylinder like this, the ideal situation where you have a fluid that is going in streamline like that, and now we need to find out, for example, the friction pressure drop because of the resistance. So imagine the fluid is moving this way and the sphere here is fixed, or the fluid is stagnant and the sphere is moving, right? So same kind of effect, right? So one thing that we didn't talk about when we talk about the drag coefficient is what will be the distribution of the shear forces over the surface. Two types of distribution can be found in this kind of most of the application. One distribution is based on an inviscid type of fluid, so fluid there is no viscous forces between the fluid itself, right? And one that is real, where we are expecting some what we call it separation at the back of these of these sphere, right? So you can see here the layer where it's close to the surface, we call this is a boundary. The boundary layer, and this is where the most friction is happening. And as you go far from the surface, the velocity is becoming almost constant. So you can see here the velocity distribution here is significant, and then after in a certain distance, there is no variation of these velocity. Changes of the pressure distribution around the sphere is impacting the total resistance of the sphere. Remember, this sphere is moving in the horizontal direction, or the fluid is moving around the sphere in the right direction, right? So how to determine the distribution of the pressure is by basically measuring the pressure forces at every point on these spheres. We measure the pressure here, 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 and so on, right? And then we plot the distribution of this pressure at every single point with angle theta. So if you can imagine that this is your theta, right? At every point here, you are measuring the pressure around the sphere. What you can do at the end is get what we call it the pressure distribution around the sphere, okay? So for an ideal case, when you have an ideal viscous, ideal fluid, you will have a distribution of the pressure that is symmetrical like this. As the angle is changing, you will see, like, you know, a symmetrical distribution of the pressure, similar to this case here, right? But when you are actually, you know, you have a real fluid that is moving around the sphere and we are measuring the actual pressures, you will see a variation from this ideal condition that is going like that. What is this telling you? Or like this, depend on the velocity of the fluid. What is this telling you? That the distribution of the pressure around this sphere is not symmetrical, okay? Let me ask you a question now. If I have a pressure distribution that is symmetrical for these fluids, like in, you know, for pressure, for example, here and here. If you have a symmetrical distribution around the sphere here, what will be the forces, the resultant force in the x direction? 0. How about vertical direction? 0 as well, right? But what happened because of the non-symmetrical pressure distribution around these bodies, you might see some resultant force, right? And this resultant force will say this force will, you know, one component maybe in this direction. Okay, so this is F resultant. Okay, there's going to be some 2 components, right? 1 and then 1 like this. Okay, so if I have a resultant component like this, so it has, you know, or the resultant forces like this, we have a component here in the x direction, so FR x and FR y. Okay, what does FR x mean? FR, this fluid is moving like this. So what is basically resisting the motion of this sphere? Which component is resisting this motion? Which one of these components are resisting the motion? FRX, right? So we have a resistant force in the x direction that is in the opposite of the fluid motion, right? So which means that this is kind of, you know, resulting into a drag force into the x direction, or a resistance force in the x direction. And what the Fy is doing? What is Fy is doing? So resisting the y direction, yeah, okay, or holding the cylinder, yes, which is what we call it the lift force. Okay, so imagine now we have, like, you know, of course this is a cylinder, right? We don't have like a very nice streamlined type of bodies. So if we imagine we create, like, you know, something like this, I want to just, like, yeah, so this is kind of like, you know, a cross section of an aeroplane wing, right? So now there's going to be some forces here in this direction and some forces in this direction here, right? So the one that is in this direction, this is what we call it the drag force, right? This is a drag force, and this is, like, you know, or let me just write it in. Drag, and this is what we call it the lift force. Okay, so we can really generate force distribution or pressure distribution by moving a certain body in a fluid in order to create what we call it the, you know, the form drag, and this form drag now is there's one is pressure drag, and there is one that is, we call it the lift force, right? And that's why you see, like, when you are landing or taking off with an airplane, this wing is taking different angle. We call this angle is angle of attack, because you'd like to change the lift force, right? So if you are kind of slowing down and landing, you are kind of increasing the this frontal space or frontal area of this air wing in order to increase the drag to stop the airplane. Okay, and you don't need that much of the lift, so that's why the plane is going down. But when you are actually taking off, you want to create these enough lift, right? So you need to have a speed, and you need to reduce the drag, but also increase the amount of lift in order to lift the airplane, right? So the pressure distribution around surfaces is very important in the design on the airplane or rockets and other things. Not only in the gas, but also in the liquid. For example, when we were talking about the pumps that we discussed in chapter 11, the centrifugal pump. Those centrifugal pump is made of blades, and this blade is taking a certain shape. So you can imagine the fluid around the surface of the blade is also exert some forces on these blades. So you need to study what will be the drag forces for these impellers and so on. What about stalling? It isn't the opposite of the lift, right? So again, it's all depend on how you look at the fluid. Are you talking about the wing that is moving and the fluid is stagnant? The aeroplane is moving in the 30,000 feet above, and might be some slow wind over there, but technically you can say, oh, this is a kind of a stagnant flow. The speed of the aeroplane is much faster than the fluid itself, right? So it's all depend on, are you looking at the fluid direction or the surface direction. So pressure distribution at the front is considered to be also a frontal drag. Like imagine yourself are walking in a windy day and against the wind, right? So if you increase this, your size, like, the frontal size of your body, right? If you are wearing like a jacket and you are holding the jacket like this way, you are kind of feeling this kind of resistance because of the form drag, okay? And this is what we call it the pressure drag. And that's why in order to move, inside this wing, what you're gonna do, you try to tilt and go in a smaller frontal area, right? Because you need to reduce the frontal drag or the pressure drag on your body, right? So imagine this, like you're holding a surface at the front of the wind, you will see a huge forces coming from these pressure drag. So these two drags, the coefficient or the pressure drag, it is so difficult to pay attention. I don't know how. Is that for me? Is that question for me? Oh, okay. Sorry. So there's two type of drag, right? So one is the friction drag. So this friction drag is coming from the viscous forces between the fluid and the surface. And the other one is the pressure drag, which is the distribution of the pressure. Some of the pressure distribution is able to lift or kind of produce the function where you are actually designing this, this equipment for, like, for example, the wing of the aeroplane. So some of the pressure distribution is designed in a way, or this we call it the aerofoil, or the shape of this cross section of the plane wing. So we call this is kind of, the distribution of the pressure around the wing is helping to create this amount of lift force. That's why we are interested to maximize lift and reduce drag in these kind of machines. A truck would have lots of pressure drag. That's totally a very good comment. But the thing is, like, it's all trade-off. Like, for truck, you need like these bigger frontal area because you are carrying loads, right? So, but there are some tricks in order to reduce the drag of these trucks, and I'm going to show you maybe some of these at the end of this slides. Okay, I will stop reading the comments because I want to just focus on the next few ideas, and then I can come back and respond to the questions. So again, like, a drag coefficient, if you remember, every time we are talking about non-dimensional form of the property that we are interested in, the only way we are doing this, if you remember in chapter 5, because we might need to do a prototype and we experiment these prototype. We put it in the lab and we measure all this. So coefficient drag is much better, representation of the drag force, because this is a non-dimensional representation of the drag force. And we divided here by half rho v square area, and this is just like, a normalizing, or like, what we call it, a non-dimensional form of the drag force. Okay, frontal area is an extremely important area when we are talking about drag, same as Blasius here, where he mentioned the truck. So frontal area is important when you are dealing with this missiles, projectiles, and all that. This is very important to keep in mind, like what will be the drag force due to the frontal area. So again, different type of area that we are talking about here, frontal area, and then there is another one, we call it the plantar-form area, which is like, when you are looking at it from above, or the planar kind of planar way of looking at the surface. And this is very helpful when we are talking about friction. And then the wetted area, this is another definition available in the flow around surfaces. And this is kind of more of surface, because some of the surface, when we are talking about here, like, wetted area, mean part of the surface is immersed in the fluid and the other part is not. Same as, for example, the ship. Like, when you have part of the surface is in touch with the liquid and the other part is outside of this liquid. So considering the wetted area here as another definition when we are dealing with area of surfaces immersed in a fluid. I talk about this, in very briefly, but, something to keep in mind that in this case, when we are dealing with drag and lift, okay, at the end, we need to find out what will be the different, form of drag or drag coefficient and lift coefficient. So there's two element of forces affecting the surfaces externally. So the fluid around the surface will be subjected to two type of forces. These two forces can be converted into coefficients. One is the drag coefficient and one is the lift coefficient. And of course, you're trying to, optimize this ratio between drag and lift for a certain purpose of, of these device that you are talking about. If you are talking here about aeroplane, of course, it's very obvious here that you're trying to change these with what we call it the angle of attack. So angle of attack is the distance, the angle from the horizontal here, right? Or this is alpha, yes, sorry. We call it alpha here. Okay. So, and the drag coefficient and the lift coefficient will be a function of the force of the lift or the force of the drag divided by the, the kinetic energy of, of the fluid multiplied by the frontal area. I talk about this, right? So that's why this is giving us an idea about, like, now if we have a different shapes, we're expecting the drag coefficient to be different. We briefly talk about this in chapter 5. We didn't get too much into the boundary layer, but actually the analysis of the drag coefficient and the coefficient of drag is entirely important when we are studying the flow around surfaces. We did the experimental analysis in chapter 5 when we deal with non-dimensional form of different objects shape, right? So you can see here, like, this figure here, A, B, C, and D, different shape, and for different of these shape, you will have a drag coefficient that is different, and you're expecting this to be experimentally valid, as well as based on the boundary layer analysis around these and around these fluids. Okay. And that's why you will see like, different shape here. For example, the way that the flow is going around stream, and you'll see here, same frontal area, the drag coefficient here is 2, the drag coefficient here is 1.1, even though the frontal area is the same, but now the fluid around the surface is taking a different shape, right? But now you have a lot of ADs at the back. So for the same frontal area here, same as this one, this one here even 0.15. You see here the drag coefficient is even much less. And why is that? It's not only the frontal area, but now the shape of the tail of the surface. So now we are reducing the ADs at the back of this shape, which means that the drag coefficient is a function of the bound, what is happening at the boundary layer, and along the whole surface, right? From the front to the hole at the back, right? So you can see here the drag coefficient for the same frontal area here is different. And once you start having a frontal area that is very small, you'll see like, a completely different, drag coefficient as well. Okay. So streamlining or the near edge is reducing the drag coefficient by 85%. You see here, the streamlining of this here is reducing this drag coefficient from 1.1 to 0.15. Okay, so you can imagine now the effect of even like, the eddy or the turbulence at the back of this surface is affecting the drag coefficient. Okay. Okay, the AD current creates low pressure area, which creates vacuum resulting in a drag. That's correct. Like, because remember when we were talking about the drag and lift are all related to two types of forces. One is friction, the other one is a pressure force. Okay, so the pressure force, of course, will be affected by the eddies. So in this case, if you are measuring the pressure at every point, this eddy is creating some, lower pressure region where basically is creating, negative forces or the vacuum pressure here, and this create like, or impacting the drag value. Similar, idea when you are talking here about swimming. Okay, of course, the position of the the person who is swimming and how he's actually streaming line inside the water will make a lot of difference to the resistance of these of his motion, right? So you can see the difference between the position in the first, the top picture and the bottom picture here. The more eddies that you are creating here, the much more drag that you are kind of facing, and then the more power that you need in order to the more power needed in order to push your body in the direction of motion, right? So drag forces is a critical in this case, and the orientation of the body is and the eddies around this body is affecting these resistant forces. You can look at this from the nature as well when you look at the design of palm trees, or like how the birds are flying in certain shapes in order to reduce the total drag over the the group of the bird that is flying. So in this case, this shape is preventing resistance, and that's why you will see some of the bird will take the front the front seat, and then after some time they get tired because of the too much resistance, while they go back and then the other the front just to exchange position in order to exert some forces for the total group to fly in a certain direction. So I want to skip this part here, but if you remember, we brought this chart in chapter 5, and we talk about different shape will have different coefficient of drag. Okay, and those coefficient of drag can be determined experimentally in the lab, but also can be determined by some understanding of the boundary layer around these bodies. Okay, of course, these number that you see here in this table are verified number using experimental and analytical work done in for flow around surfaces. And those are the very common shape that you can find available in the fluid mechanics kind of research, right? So expecting the frontal shape of the body will affect the drag. The shape itself of the body will affect the drag coefficient and so on. And you can see this, as you keep going to a human body, to a truck, and so on, right? Many ideas. And this is one of the figures that we presented in chapter 5 by looking at what we call it the streamlined type of car. So back in the 19th century, the beginning of the 19th century, you'll see the car is taking this box kind of shape. And by the time you are kind of, increasing the speed of the car, improving the performance of these cars, and, optimizing the energy produced by the engine, you start shaping the car into taking a different shape in order to streamline the shape of the car to reduce the drag coefficient on this engine. As I mentioned, some of the time you cannot do this. For example, for trucks, because you need to fill this, right? You need to have this box. You need to fill this, right? So basically, you need to have this bulk shape of the truck. But what you can do, you can have some kind of deflector, and this deflector and the shape of the entrance, or the frontal area of the car is kind of reducing as much as you can, like these frontal pressure drag created by the fluid around the bodies. What I want you to know from this chapter is basically what we just discussed today. Like, I just need you to be aware of what is boundary layer is, what is a different type of forces affecting surface if the fluid is moving around the surface. What is the name of these forces? We said drag forces and lift forces, right? Shape of the bodies and the frontal area of these bodies affecting this drag, right? Reynolds number is one of the very important parameters to characterize this type of boundary layer thickness. There is something called boundary layer thickness, and this thickness is a different location around the surface is taking a different value. And this value, we call it delta, and this delta could be function of Reynolds number, as we mentioned. We don't want to increase the drag here, like we are trying to reduce the drag here, Jacob. So if you, because if you don't have this deflector here, you might see some of eddy losses here. Try to minimize these eddy losses. So we're trying to minimize the drag over the truck. Does that make sense? Yeah. So, but as I mentioned, you have a limitation on like how much you can do in terms of the frontal area. So you have a bigger frontal area of the truck. You try to streamline some of the part of the truck in order to, minimize eddies that is generating negative or adverse pressure that is contributing to the more of the form drag. Form drag means pressure drag. Okay. This is basically cover what I need to present in chapter 7. I don't want you to go beyond what is presented in these materials. Just to keep in mind this very general definition of element that we study for this chapter. So next time we're gonna talk about open channel flow. I know this is not a topic that is of interest of many, but again we're gonna introduce major concepts, like main concept when we studied open channel flow. Any questions? Yeah, I would say very minimum in these chapters, right? This is just like an overview chapter, so that's why I think it will take you 30 minutes to study for this chapter. So that's as we just presented now. I just want you to be aware of this, these topics. So it's not going to be completely strange for you when it's mentioned: boundary layer thickness, drag force, friction for skin friction drag, form, drag form, or pressure drag. This is a kind of thing that I want you to be aware of, right? I promise you in this course that we are just opening or scratching the surface on the fluid mechanics subject, but I'm sure that, you know, once you start getting into more interest in very specific topic, you will search yourself and learn for yourself about this, or maybe taking different courses to expand your knowledge about these subjects. Any questions? Let me stop recording here, and I will be available to answer any of the questions you have.